Hey guys, so far this chapter we've been playing a lot with exponents. Today we're going to actually graph with some exponents, specifically when the variable x is the exponent. So let's go ahead and hop to an example here. You guys know me. I like to just do examples here, and I like those call and response things. We're going to get to a point where I say graph, you say table. So here's the table I want you to make. X, y, -2, -1, 0, 1, 2. And we're going to talk about when you might change that here in a minute. Oh, by the way, these are some rules that we have to follow up here. I'll go ahead and highlight those for you. A cannot equal 0. A and B are going to be normal numbers. B has to be bigger than 0, but also B can't equal 1. So, okay, so if I take my calculator and I plug these in, this is the formula I'm working on right now. Then I have 7 to the -2nd power. I used my calculator. It is 0.02. Next, I did 7 to the -1st power, which was 0.14. I did 7 to the 0 power, but I remembered that anything to the 0 power is 1. Anything to the 1st power is itself. And 7 squared is 49. And now you're going to graph those the best you can. It's not going to be perfect, okay? Or at all, apparently. Come on, buddy. There we go. 1, 2, 3, 4, 5, 6, 7. Excuse the fact that this pen just does not do it well. So connect the dots. And this is what that's going to look like. If you wanted to, you could keep plugging in some of those 7s. Like if I did 7 to the -3rd, that's 0.0029. Let's maybe try 7 to the -6th. 1, 2, 3, 4. 1, 2, 3, 4, 5 zeros, and then an 8, 5. If I keep plugging in, you're just going to keep getting smaller and smaller and smaller decimals. But it's never going to actually meet 0. So that's the cool thing about exponentials. It's kind of like our greater than or less than, where it's going to get really, 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 really close, but it's never going to actually touch. So, by the way, that is called an asymptote. I'm going to draw that in green here. Asymptotes are that line where your graph is going to approach, but never actually equal. That's called an asymptote. Let's try another example. See if you notice a difference this time. And so this time I say graph, you say table, and we're just going to kind of stick to a generic table for now and see what we get. So 1/2 to the -2nd power is 4. 1/2 to the -1st power is 2. Anything to the 0 power is 1. And then if it's to the 1st power, it's just itself. And then finally, 1/2 squared is going to be 1/4. So let's graph this one. -2, 1, 2, 3, 4. -1, 2. 0, 1. 1 and 1/2. And 2 and 1/4. Okay, if you want to maybe find some more values, like maybe I'm going to plug in to the -3rd power. Oh, I forgot to do the -1 this whole time. Sorry, guys. I'm going to have to erase all this. So this is going to become 3, 1, 0, -1/2, -3/4. Whoops, I forgot about that -1 on the end. So let's regraph. -2 and then up 3. 1, 2, 3. -1 goes to 1. 0, 0. Oops, didn't mean to make 2 dots there. 1, -1/2. And 2 and -3/4. So if you keep doing values, what you're going to find this time is that the shape, hopefully, if I can get that dot to go, is going to end up kind of looking like this. And this time it flattens out right here at -1. The asymptote this time is at -1. Oh, wait a minute. What do you notice about the original equation and my asymptote of -1? That number right there tells you where the asymptote is. So that's pretty cool. Oh, another thing you might notice, I did say B has to be bigger than 0 right here. Oops, that's the wrong thing. B has to be bigger than 0. And then also B can't equal 1. That's kind of a turning point for the graph. So check it out. Here the B value was 7. That was a nice happy number. Here it's 1/2. That's less than that 1 value. Notice the difference in the ways the graphs look. Turns out that's how it always is. If B is between 0 and 1, we call that exponential decay because it's going down. And if it is greater than 1, we call that exponential growth because it's growing up towards the sky. And again, that's as you read the graph from the left to the right. That's how we read graphs. So one way we can figure out, this is the last example, one way we can figure out if something has exponential behavior or not is to take the items divided by each other. So I'm going to take 16 divided by 12. That is going to be a fraction. I want you to simplify that, but leave it as an improper fraction. So it is 4/3. I want you to do that to all of these. If they're the same, it's exponential. If they're different, it's not exponential. So what I try next is 20 divided by 16, or 20/16, and I try to simplify that. This time what I get is 5/4. That's already different, so no, it's not exponential. Your explanation is your work.